These are the only close-up images of Neptune ever taken. Every single one of them was captured by the same spacecraft in 1989. Before that, Neptune was a blur. But here is the problem. NASA altered the color. The deep, vivid blue that made Neptune look so dramatically different from Uranus was an artifact of image processing. In reality, both planets are a pale, greenish blue. And that's just the beginning what actually hides in Neptune's images. Neptune's atmosphere turned out to be one of the most dynamic and violent in the entire solar system. The photographs revealed a massive storm in the southern hemisphere, an oval-shaped vortex roughly the size of Earth. The Voyager team dubbed it the Great Dark Spot. Around its edges, winds were measured at up to 1,300 miles per hour. Those are the fastest winds ever recorded on any planet. For context, the most powerful hurricanes on Earth produce winds of about 250 miles per hour. Neptune's winds were more than 5 times stronger. But here is the strange part. Neptune receives almost no energy from the sun. It sits so far away that solar heating is negligible, and yet it has the most violent weather in the solar system. The data showed that Neptune radiates roughly 2.5 times more energy than it receives from the sun. Something inside the planet is generating enormous amounts of heat. To this day, the exact source of that internal energy is not fully understood. Above the Great Dark Spot, Voyager captured high-altitude clouds of frozen methane, streaking across the atmosphere like cirrus clouds on Earth. But unlike Earth's clouds, which are made of water ice and last a few hours, Neptune's methane clouds persisted for at least 2 full rotations of the planet, more than 36 hours. The spacecraft also confirmed something observers on Earth had long suspected but could never prove. Neptune has rings. 5 of them, in fact, composed mostly of dark dust. And in the outermost ring, named Adams, something genuinely puzzling was happening. The material in the ring was not spread out evenly, as physics would predict. Instead, it was clumped together in distinct arcs, 4 of them, named Liberté, Eagerlight, Fraternite, and Courage. The laws of orbital mechanics say those arcs should spread out and dissipate. They haven't. Scientists now believe the gravitational influence of the small moon Galatea, orbiting just inside the ring, may be stabilizing them. But that explanation remains a hypothesis. On August 25, 1989, Voyager 2 made its closest approach to Neptune. It passed just 3,408 miles above the planet's north pole. That was closer than the spacecraft had come to any planet since leaving Earth 12 years earlier. The images transmitted back to the Jet Propulsion Laboratory in Pasadena, California, took 4 hours to travel across 2.9 billion miles of space. When they arrived, team members crowded around computer monitors to see them. There was no internet in 1989. No way to broadcast the images to the world in real time. They were available at only a handful of locations on Earth. But the team shared what they found as quickly as they could. Now, Voyager also discovered something deeply unusual about Neptune's magnetic field. On most planets, the magnetic field is roughly aligned with the axis of rotation. On Earth, for example, the magnetic poles are close to the geographic poles. Neptune's magnetic field is tilted about 47 degrees from its rotation axis, and it is significantly offset from the center of the planet. The field is about 27 times more powerful than Earth's. And because of that extreme tilt, Neptune's magnetosphere reconfigures itself with every rotation, flipping between an Earth-like orientation and a pole-on configuration. The charged particles inside follow wildly complex paths, creating structured auroras and radio emissions unlike anything seen at the other giants. No one fully understands why Neptune's magnetic field behaves this way. 5 hours after closest approach to Neptune, Voyager 2 turned its cameras toward Triton, Neptune's largest moon. The last solid body the spacecraft would ever explore, and the encounter did not disappoint. Triton is a world of contradictions. It is the seventh largest moon in the solar system, with a diameter of about 1,680 miles. It is slightly larger than the dwarf planet Pluto and nearly identical in composition. Both are covered in frozen nitrogen, methane, and carbon monoxide. Both likely formed in the same region of the outer solar system. But while Pluto still drifts freely through the Kuiper belt, Triton was captured. At some point in the distant past, Neptune's gravity seized it and pulled it into orbit. We know this because Triton orbits Neptune backwards. It revolves in the opposite direction to the planet's rotation. This is called a retrograde orbit. No large moon in the solar system does this except Triton. And the physics is clear. A moon in a retrograde orbit cannot have formed alongside its planet. It must have come from somewhere else. The leading hypothesis, supported by numerical simulations, is that Triton was once part of a binary system, two objects orbiting each other as they drifted through the Kuiper belt. When this binary passed close to Neptune, the gravitational interaction ripped the pair apart. One object was flung away on a hyperbolic trajectory, lost forever to interstellar space. The other, Triton, was captured. A 2024 study of the chemical compositions of Pluto and Triton found that both bodies share large amounts of nitrogen and trace amounts of methane and carbon monoxide, consistent with a common origin in the outer regions of the young solar nebula. But here is what made Triton so astonishing to the Voyager team. Despite having a surface temperature of roughly -391 degrees Fahrenheit, making it the coldest surface ever measured by the spacecraft, Triton was not a dead world, it was active. Voyager's cameras revealed a surface with remarkably few impact craters. In geological terms, that means the surface is young. Some regions are estimated to be no more than 6 million years old. Others perhaps 50 million. That is extraordinarily recent for a body in the outer solar system. The images showed a terrain unlike anything seen before. Vast, icy plains dotted with pits, complex ridges and furrows carved by freeze-thaw cycles, and a bizarre formation the team called cantaloupe terrain because it resembled the skin of a cantaloupe melon. It covered much of the Western Hemisphere, made of dirty water ice, pocked with smooth depressions about 30 to 40 kilometers across. The leading explanation is diapirism, the slow upwelling of less dense material through denser layers above it, like a lava lamp made of ice, operating over millions of years. And then there were the geysers. Voyager 2 observed plumes of nitrogen gas and dark dust erupting from beneath the surface, shooting up to 8 kilometers high. Triton is one of the few bodies in the entire solar system on which active eruptions of any kind have been directly observed. One hypothesis suggests that sunlight passes through a transparent layer of nitrogen ice on the surface, warming the darker material beneath. As that material heats up, the nitrogen sublimated, building pressure until it erupts through the ice like a cap blowing off a bottle. A solid greenhouse effect. This model is supported by the observation that Triton was near its peak southern summer at the time of the flyby, meaning its south polar cap was receiving prolonged sunlight. But some researchers believe the plumes may be cryovolcanic, driven not by sunlight, but by internal heat. Triton's estimated plume output may exceed 400 kilograms per second, comparable to the geysers of Enceladus. One of the largest cryovolcanic features found on Triton is a caldera-like structure called Leviathan Patera, roughly 100 kilometers in diameter. Surrounding it is a massive plain of cryovolcanic material spanning at least 490,000 square kilometers. Connected to the caldera are two enormous lakes of cryolava, believed to be primarily water ice mixed with ammonia. While they were molten, these lakes would have qualified as stable bodies of liquid water on a surface beyond Earth. That is extraordinary. Triton is the only icy body known to feature cryolava lakes. If there is enough radioactive decay in Triton's rocky interior, it could maintain a liquid subsurface ocean to this day, hidden beneath a crust of frozen nitrogen and ice. The black material ejected by the plumes is suspected to contain organic compounds, and if liquid water is present beneath the surface, some researchers have speculated that Triton could be habitable for some form of life. That remains speculation, but it is the kind of speculation that keeps planetary scientists awake at night. We do not know for certain. Voyager 2 only imaged about 40% of Triton's surface, the rest remains unseen. Now, remember the Great Dark Spot. That massive storm system the size of Earth, spinning in Neptune's southern hemisphere with 1,300-mile-per-hour winds. In November 1994, the Hubble Space Telescope turned toward Neptune to photograph the storm again. It was gone. Completely. Not weakened. Not shifted. Vanished. Unlike Jupiter's Great Red Spot, which has persisted for at least 300 years, Neptune's storms appear to be transient. They form, they rage, and they disappear, sometimes within just a few years. When Hubble looked again, a new dark spot had appeared in Neptune's northern hemisphere, a near mirror image of the original, but in the opposite hemisphere. Since then, multiple dark spots have come and gone. In 2018, Hubble documented a dark spot from its very birth, the first time that had ever been achieved. That storm was smaller than the original, but still larger in diameter than the Atlantic Ocean, at approximately 4,600 miles across. In August 2020, one of these spots did something no one predicted. It had been drifting southward, toward the equator, where models suggested it would dissipate. Instead, it suddenly stopped and reversed direction. Around the same time, a smaller companion storm appeared nearby, which astronomers dubbed Dark Spot Junior. Some researchers believe the reversal of the larger storm may have been related to the birth of the smaller one, but the mechanism is still under investigation. What makes this even more perplexing is the question of energy. Where does the power come from to drive these enormous storms on a planet that barely receives any sunlight? Neptune radiates about 2.5 times more energy than it gets from the Sunday. Some researchers believe this internal heat source is leftover warmth from the planet's formation 4.5 billion years ago. Others point out that this explanation does not easily account for why Uranus, a planet of very similar size and composition, radiates almost no excess heat at all. The two ice giants should behave similarly. They do not. And nobody is entirely sure why. So what do the images of Neptune actually hide? The answer is almost everything. Voyager 2 did not carry a near-infrared spectrometer. That means we have no detailed chemical map of Neptune's atmosphere at depth. We do not know the three-dimensional structure of its cloud layers. We do not understand the composition of its core or how large it is. We cannot explain why its magnetic field is so wildly offset and tilted. We do not know how its ring arcs maintain their structure against the forces that should destroy them. And the images themselves were not even what they appeared to be. In 2024, researchers reprocessed the original Voyager 2 photographs and discovered that Neptune's famous deep blue color had been enhanced. The Voyager team had adjusted the images to better reveal clouds and atmospheric features, pushing the contrast beyond what the eye would naturally see. In reality, Neptune and Uranus look much more alike than the iconic images suggested. Both are a pale, greenish blue. The striking azure of Neptune, the image that defined the planet for a generation, was partly an artifact of image processing. We also know almost nothing about what lies beneath those clouds. Neptune is classified as an ice giant, one of two in our solar system alongside Uranus. Most of its mass, more than 80%, is thought to be a hot, dense fluid of water, methane, and ammonia above a small rocky core roughly the mass of Earth. Scientists believe there might be an ocean of superheated water deep inside Neptune, kept in a liquid state not by temperature alone, but by the immense pressure bearing down on it. It does not boil because the pressure will not allow it. But we have no direct measurements of any of this. No probe has ever entered Neptune's atmosphere. No orbiter has ever circled the planet. Everything we know comes from that single flyby, from Hubble observations across billions of miles, and from models built on incomplete data. After the Neptune encounter, Voyager 2 kept going. It continued to study the planet until October 2, 1989. In all, it returned more than 9,000 images of Neptune, its rings, and its moons. Then it turned its cameras off. The imaging system was disabled to conserve power. It has never been turned on again. The spacecraft entered what NASA called the Voyager interstellar mission. Over the following decades, instruments were shut down one by one as power dwindled. The scan platform and ultraviolet spectrometer were terminated in 1998. The digital tape recorder went dark in 2007. The planetary radio astronomy experiment was powered off in 2008. And still, Voyager 2 kept transmitting. Its 13-watt signal, weaker than the light in a refrigerator, continued crossing the void. On November 5, 2018, 6 years after its twin Voyager 1, the probe crossed the heliopause, the boundary where the Sun's influence ends and interstellar space begins. It became only the second human-made object to enter the space between the stars. As of early 2026, Voyager 2 is more than 13 billion miles from Earth, moving at about 34,000 miles per hour relative to the Sunday. It communicates exclusively through a single antenna near Canberra, Australia. In July 2023, a programming error misaligned Voyager 2's high-gain antenna by 2 degrees, breaking communications with Earth. For days, silence. Then, on August 1, the Deep Space Network detected the spacecraft's faint carrier signal using multiple antennas. On August 4, a high-power command was sent from the Canberra station, what engineers called a shout across the void, and it worked. Voyager 2 reoriented itself toward Earth and resumed contact. But Voyager 2 is dying. Its 3 radioisotope thermoelectric generators, powered by decaying plutonium, provided 470 watts at launch. That power halves roughly every 88 years. In 2023, engineers found a way to reroute power from a backup voltage regulator to keep instruments running a little longer, but it is a temporary measure. The plasma science instrument was turned off in October 2024. The low-energy charged particle instrument was terminated in March 2025. The cosmic ray subsystem is projected to go dark in 2026. By around 2030, there may not be enough power to run any instruments at all. By 2036, Voyager 2 is expected to fall out of range of the Deep Space Network entirely. Some of the thrusters needed to point its antenna toward Earth are clogged. There are no backups left. As Voyager's project manager at JPL acknowledged, everything on board is running on single string. One failure in the wrong system and contact is lost forever. And right now, in 2026, there is no spacecraft en route to Neptune. There is no approved mission, no probe being built. The planet sits in darkness at the edge of the solar system, unexplored by any technology built in the last 4 decades. 2 mission concepts have been proposed. One, called Triton, was a flyby mission focused on Neptune and Triton, but it lost out to 2 Venus missions in 2021. Another, called Neptune Odyssey, is a flagship orbiter concept targeting a 2033 launch and a 2049 arrival. There are also smaller proposals, a new Frontiers-class Triton Ocean World Surveyor that could launch in 2031 and arrive in 2047, and a concept called Nautilus. None of them are funded. None of them are certain. Neptune and its captured moon Triton remain among the least understood major objects in our solar system. They are unexplored with modern instruments. We do not know whether Triton has a subsurface ocean. We do not know the depth or composition of Neptune's core. We do not know what drives the fastest winds in the solar system on a planet that barely sees the Sunday. We do not know why its magnetic field is so strange, or why its storms appear and vanish on timescales of years, or how its ring arcs defy the laws that should scatter them. And Triton itself may hold secrets we cannot even imagine. Its cryovolcanic features, its possible ocean, the organic compounds in its dark plume deposits, all of these make it one of the most compelling astrobiological targets in the solar system. A captured dwarf planet, shaped by tidal forces and radioactive heat, with the chemistry and the energy to potentially support something we have not yet found anywhere beyond Earth. All of this from a single flyby. A few hours of data collected by a spacecraft running on the power of a refrigerator light bulb 36 years ago. The Voyagers carry gold-plated records containing the sounds of Earth, greetings in 55 languages, and music from across human history. Instructions on how to play the record are etched into the surface. NASA has said that the Voyagers are destined, perhaps eternally, to wander the Milky Way. In roughly 42,000 years, Voyager 2 will pass near the star Ross 248. In 296,000 years, it will drift past Sirius, the brightest star in our sky. By then, whatever is left of the spacecraft will be unrecognizable. But the golden record will endure. And somewhere behind it, 2.8 billion miles from the Sun, Neptune will still be spinning, still wrapped in those pale blue clouds, still hiding everything we have not yet learned to see. For now, all we can do is look from a distance and wonder what is waiting there in the dark.